As manufacturing scales down to the 2-nanometer level, the primary threat to a functional chip is no longer the machinery, it is human biology. An average human adult sheds roughly 200 million skin cells every single hour. This diagram illustrates the physical mismatch at play here. On the left is a typical human skin flake, measuring roughly 30 micrometers across. On the right is a 2-nanometer gate-all-around transistor wireframe. The biological debris is astronomically larger than the hardware. Because of this extreme size discrepancy, traditional cleanrooms built around human workers become physical liabilities. Maintaining absolute purity at the atomic scale requires an entirely different approach to factory isolation. The industry's proposed solution is often called the dirty fab. The concept involves eliminating massive macro-level cleanroom standards in favor of cheaper, highly automated facilities.
There is a misconception that a dirty facility simply means shutting off the HEPA filters and replacing technicians with basic conveyor belts. The reality is dictated by the gate-all-around transistors architecture. These vertical silicon nanosheets are highly fragile. A human cell is 15,000 times larger. If one skin flake lands on wafer, it acts like an asteroid impact, crushing thousands of circuits instantly. Securing a manufacturing environment capable of preventing this exact failure rate requires a starting capital investment of roughly $25 billion. The math forces a strict engineering conclusion. You cannot filter the air enough to safely accommodate breathing, shedding operators. You must completely remove human biology from the production floor. Transitioning to 100% robotic orchestration is an absolute physical necessity for atomic-scale manufacturing to function. If the factory floor is completely unpurified, the physical wafers must still remain pristine throughout their entire journey. The primary mechanism for this micro-isolation is the front-opening unified pod, or FOUP. Rather than cleaning the entire building, the FOUP acts as a sealed, highly controlled mini-environment that securely transports batches of wafers directly through the dirty air of the factory. This minimalist 3D model of a FOUP highlights its internal pressure logic. Notice the outward-pointing vectors. The internal pressure of the pod is constantly maintained at a higher level than the external factory floor. If a microscopic gap occurs, the air pushes outward, physically blocking external particulates from entering. But the system faces a critical vulnerability. Every time a FOUP arrives at a processing machine's load port and is forced to open its doors, the exact moment the pod docking, a high-velocity nitrogen purge sequence initiates. This nitrogen curtain creates an invisible, pressurized shield against the surrounding atmospheric air. A successful dirty fab relies on shifting the massive filtration burden from a facility-wide HVAC system directly down to these localized, pressure-controlled airlocks. To finalize the airlock sequence, the system must actively monitor the chemical composition of the seal before the inner tool door is allowed to open. This readout shows the strict threshold requirement. The tool's airlock remains locked until the internal oxygen levels drop below 1,000 parts per million. If the system misses this threshold by even a fraction of a percent, the 2-nanometer wafer is exposed to ambient oxygen for a millisecond. That is enough time to induce atomic-level oxidation and destroy the entire batch. Once you solve for physical particulate contamination and oxygen, you are left with an invisible, highly destructive threat: temperature. Standard cleanrooms use strict laminar flow systems to maintain perfectly even temperatures. By removing those massive HVAC systems, the factory introduces severe thermal variables. This introduces thermal jitter, an invisible force that physically warps the silicon. The baseline material science is visualized here. Silicon possesses a specific linear thermal expansion coefficient of 2.6 times 10 to the negative 6th per Kelvin. When we apply this abstract math to the surface area of a standard 300 millimeter wafer, the results are highly problematic. A temperature shift of a single degree Celsius causes the wafer to physically expand by roughly 780 nanometers. In macro engineering, 780 nanometers is negligible. In a process manufacturing 2-nanometer gates, it is a massive structural deformation.
A fractional degree of thermal variance in the factory's air currents will physically stretch the silicon far beyond its usable dimensions. Modern lithography requires printing dozens of atomic layers sequentially. Each new layer must stack perfectly on top of the previous one. For 2-nanometer logic, the absolute limit for alignment tolerance is less than 0.5 nanometers. When a 780-nanometer thermal expansion force pushes against a 0.5 nanometer alignment tolerance, the layers miss their marks entirely. The ultimate challenge of automated chip production is not sweeping up dust. It is maintaining absolute thermodynamic stasis to prevent a 0% yield failure. Managing micro-isolation and absolute thermodynamic stasis simultaneously across a building the size of a city requires severe digital oversight. The brain of the operation is the Manufacturing Execution System, or MES. This wireframe displays the MES's commands in action. The yellow nodes represent overhead hoist transports, routing the sealed FOUPs across a high-speed ceiling grid. These transports are programmed to move at exactly 3 meters per second, strictly limiting the time a pod spends exposed to the ambient environment. The MES enforces a rigid parameter known as Q time, the maximum allowable duration a wafer can sit idle waiting between machine cycles. If a wafer exceeds its Q time, airborne molecular contamination begins outgassing directly from the plastic walls of the FOUP itself, ruining the silicon. High-speed, AI-driven orchestration is the only mechanism fast enough to beat the physical clock against chemical outgassing and thermal drift. The math leaves no margin for error. We are balancing 30 micrometer skin cells, strict 1,000 part per million oxygen thresholds, and 0.5 nanometer thermal tolerances. Operating a fab without cleanroom standards is a complex exercise in extreme micro-isolation and thermodynamic control. It is a highly tuned physical system. Relying on 100% robotic orchestration is an inescapable consequence of atomic-scale physics. In the era of 2-nanometer computing, extreme engineering means acknowledging that the natural environment is simply too hostile for human presence.